Swayam Prabha. Digital India. Educated India.
Today we will talk about one of the most common toy models in polymer physics, that is called the freely jointed chain, and then we will build more different types of random walk models. So, as I have already said in the introduction classes, that one of the problems we are interested in is the end-to-end distance of polymer chain, which we refer to as the RE, and I already told you that we do not typically look at a particular conformation, because a polymer chain can take many different types of conformation. So, what we look at is not the RE of a particular configuration, but some sort of an average RE of many possible conformations. Okay. So, what we will try to find out is the mean end-to-end distance, and I will show you that in these models the mean end-to-end distance becomes 0. So, what is more important is the squared mean of the mean end-to-end distance. Okay, so we will try to find this particular quantity. Now, there are two ways to find this average that I want to clarify in the very beginning. So, when I write an average like this is known as the ensemble average, an ensemble meaning that it corresponds to many conformations. So, we look at all possible conformation in principle, compute RE for those conformations, and then take an average of this. Okay. So, when I look at this average property, I can find in two ways. One way is like I look at one polymer chain in the system with as a function of time. So, this polymer chain will keep on changing its conformation. We compute the RE of the polymer chain as a function of time, and then do a time average. The other way to look at the same thing is, let us say we have a beaker composed of many polymer chains. We compute the RE of all the chains in the system, and then do what is known as a spatial average. Okay. So, this ensemble average can be done in two ways: a time average or an spatial average. And one of the principles of thermodynamics or statistical mechanics that becomes very handy here is, if I look at very large systems, then the time average become equal to the spatial average, which again becomes equal to the ensemble average. Systems which show this behavior are known as ergodic systems, and this particular principle is known as ergodicity principle. Okay. So, we will use that idea. It will make certain difference in some cases where ergodicity does not apply, but in most cases that we care about, we do not differentiate between the time average and spatial average. We refer to the ensemble average of any property we are interested in. Okay. So, going back to the representation of the polymer chain as a random walk, let me briefly illustrate of what exactly, why exactly the random walk represents a model of the polymer chain. Okay. So, let us go back to a polymer chain representation as a chain of carbon, and if you remember, I told you, like, between the carbons which are adjacent to each other, there is a covalent bond. So, all these bonds are my covalent bonds, which are really very strong. So, this carbon-carbon bond distance cannot really change by much. Then between say any three of these carbons, we have something known as the bond angle, which happens because there is a covalent bond here and there is a covalent bond here. If I know what a covalent bond is, it is formed by overlap of electron clouds here, electron clouds here. So, now there is interaction between the electron clouds on the two bonds that give rise to a certain bond angle. Okay. So, this is of course weaker than the bond, but it is still, I would say, quite stronger. So, the bond angle also does not change by a lot. Okay. And then if I look at say the 4 adjacent carbon, then what we have here is what is known as a torsion angle between say 1, 2, 3 and 4, and the torsion angle can be relatively weaker than compared to the bond distance or the bond angle and so on. So, if I go to say carbons which are further along the chain, the interactions will be weaker and so on. Okay. What it really means is, if I look at this kind of a polymer chain, beyond certain number of carbons, the position of the carbons distant along the chain become somewhat uncorrelated. For example, the position of C1 and C2 are very much correlated. C2 cannot just be anywhere. The position of C2 depends on C1. C1 and C3 has a bond angle. So, C3 also cannot be really anywhere. It has to be somewhat correlated to C1. C4 is relatively more free to be anywhere, but again it has to be correlated with C1. But if I go like distant along the chain, what will start to happen is this carbon and a carbon far off, their positions can become like highly uncorrelated. That means this guy can pretty much be anywhere if this guy is somewhere in the chain, because all these carbons, as I am going along the contour, the interactions between the carbons are becoming weaker. So, along certain distance on the chain, these interactions almost die off, and then we can say that this carbon is uncorrelated to this carbon. Okay. So, what I then do is I will take this entire distance and this entire distance and refer to that as a segments of my model, such that I will build my polymer model as composed of this kind of segments, where each of these segments can really move in an uncorrelated fashion, because this will correspond to certain number of carbons, of course, and this correspond to certain number of carbons, but beyond, after this much distance, the carbons have become somewhat uncorrelated, and for this reason I can use a model of a polymer chain that is known as a freely jointed chain, where segments are uncorrelated. Okay. Uncorrelated meaning that, of course, they have to be connected in the middle like a hinge, but then this guy can be like pretty much anywhere. Okay. So, let me explain this a bit more. So, let us say if this is a model of a freely jointed chain, and let me refer to this vectors as some bond vectors. So, let us say if the first one I will refer to it like a B1, second one is let us say B2, third one is let us say B3 and so on, and the last one becomes like Bm, then Bi is what I refer to as a bond vector or segment vector. This, by the way, is not a carbon-carbon bond. This bond vector represents a sequence of carbons after which the positions become uncorrelated. Okay. And so if I follow this, then this, if I start from here to there, then this becomes my end to end distance vector. And this becomes my bond vectors. Okay. So, what I really mean to say is, if I look at any particular bond vector here and the adjacent one, so let us say I look at some nth bond vector here, the next bond vector is free to be in any direction. It can be like this, it can be like that, it can be like this, like that, like that. It can even be like folding back onto the previous segment. Okay, and we will talk about this in a moment. What does the folding back mean and so on. So, Bn plus 1 is uncorrelated with respect to Bn. This really means that the Bn plus 1 can be at any angle with respect to Bn. Okay. So, now if I look at the end to end distance vector, this is sum over. So, now let us say we have capital M total segments, then this is my segment 1, segment 2, let us say I refer to this capital M, or I can also talk in terms of nodes. This is my 1, 2, 3 and so on. So, it becomes like M plus 1. So, if we have say capital M segments, then Re is sum over all these bond vectors simply by the standard vector addition rule. So, we can sum from n equal to 1 to capital M Bi, which will be same as the end to end distance vector. Okay. So, let us say if I try to find the ensemble average of this, then this will mean an ensemble average of that. So, since I am averaging over a sum, it should be same as summing over the averages. It is like a standard math at work here. So, I can write this as something like this, and now if I look at it, then these bond vectors, just like I explained, can be in any direction. So, if I look at different conformations, you will find that Bi has equal probability of being in this direction than being in the opposite direction, and that is true for all possible directions. Okay. What it really means is, if I really take an average of these bond vectors, what I will essentially get is 0, and it is it really does make sense, because the polymer chain can really take any number of conformation. Okay. So, it is equally probable to have this conformation than the opposite of this, where we have the end to end distance vector as like minus Re. Okay. So, there is no real difference between this conformation and that conformation. So, if I average over the bond vectors, I must get a 0 vector. Okay. Now, this will not be true if I try to compute the mean squared end to end distance. Okay. And why is that? Because if I do the RE square, then this will correspond to the dot product of the RE, and by the same formula I derived earlier, I can write this as something like something like that. Okay. So, keep in mind that I have used two different indices here, BL and NBM, as opposed to BI there. Actually, this should have been BN, because I am summing over all possible value of n. So, now I am using two different indices. The reason why this is important is because if I really take these two sums, we do have like cross terms. For example, think of like multiplying the sum with itself Of course, I will have terms like b naught square, b1 square and so on, but I will also have cross terms like b naught dot b1 plus b naught dot b2 and so on. Okay. So, to include the cross terms, we must be using this particular formula where I am using different indices for the two RE vectors. Okay. So, now if I do that, this becomes, by simply rearranging the location of sums, and I can do that because the second summation is independent of BL. So, I can really move the summation, this summation to there. Okay. So, again just as I said earlier, I can move summation outside and do the averaging inside. Okay. And now we have something interesting here, that if I look at this BL and BM, I am summing over all possible values of L and M. What you will see is, if L is not equal to M, then of course then BL and BM are uncorrelated. So, for any given value of BL, BM can be in any direction. For any value of BL, BM can be in any direction. So, what it really means, it is equally probable to be along this direction and its opposite, equally probable to be along this direction and its opposite, and so on. What this really amounts to is, if I average over this product, this will be equal to 0. On the other hand, if L is equal to M, then of course BL and BM are the same vector. So, I am multiplying the same vector. So, BL dot BM become equal to something like a B square, provided we assume all the segments are of a constant length B. So, then we can replace this particular sum by something like B squared, which is equal to M B square. What it really means is R E square is proportional to M. And now, since we said that I am replacing certain number of carbons by a segment, if the number of carbons increases, the number of segments also increases. So, what really it means is, just like I can say the mean R E square is proportional to M, what it also means is mean R E square is proportional to N, where N is the number of repeat units, since N by M is some constant. Okay, so we don't really care how many repeat units I use to represent a segment. The key message is the mean square displacements and the average of mean square displacement is proportional to the number of segments, and since we are representing many repeat units by one segment, the mean square displacement squared averaged should also be proportional to N, which is the ideal chain behavior I have hinted to you in the earlier classes. Okay. So, now I will do something interesting, that this is like a model where we began from the actual chain of carbons, then we tried to make a physical assumption that beyond certain number of carbons the positions of the carbons become uncorrelated or the segments become uncorrelated, and therefore we can represent them as some kind of a fairly jointed chain. What I will now show you is we can think of a very different model, I would say a much simpler model, and that also gives you the same final answer. Okay. So, going back to our discussion of TWI models, I told you that one way to do a TWI model is start from a carbon chain representation, try to build a TWI representation and then find the answer. The other way to look at it is look at like what do you want and try to build TWI models which give you the same answer. Okay. So, what I will use now is what is known as a one dimensional random walk, which is also referred as the Drunkard walk. And the idea behind this is very simple. You think of a man who is highly drunk and he has lost his senses, so, and he starts from bar and he is on the way to home. Okay. So, let us say he starts here, this is where he starts from, he does not know like where his home is, so he makes like one step to his left or to his right, and then after going there he again forgets his previous step. So, again he makes one step to the left or to the right. So, at every given time his steps are either to the left or to the right with almost equal probability, provided that he has lost all his senses, he will not remember in what direction he walked in the last step. Okay. So, in that case he will perform a walk something akin to this, provided that he is only walking left and right. So, he can make certain steps to the left, then certain to the right and so on, and then let us say if his home is somewhere far off, he may or may not reach his home, right. So, this model has nothing to do with the polymer chain except keeping the main idea that two adjacent steps of the Drunkard walk are completely uncorrelated, just like what we did in the fairly jointed chain. Okay. So, now in this case if I want to represent the segment vectors or his step vector, then that vector is either to the left or to the right. So, either it is something like plus b along the x direction, that is my unit vector in x direction, or it is say minus b in the x direction when he is going to the right and when he is going to the left, and both of them have equal probability to occur. Okay. So, now again if he is making capital M steps, then the end to end distance that he has travelled is the sum over all these steps. Okay. So, now if I take an average over this, by the same kind of a rule, I do get something like this, and again the ensemble average of any particular step will again be 0, because he can go to the left or to the right with equal probability. So, this must be equal to 0, and so again the average of the end to end distance vector must be equal to a null vector. Okay. Now, again if I do an RE squared average, I do have a very similar formula. And again you can see that if L is not equal to M, BL and BM represent two different segment vectors or step vectors which are completely uncorrelated. So, provided he moved to the left in step number 2, in step number 3 or step number 5 he can move both to the left or to the right with equal probability. There is no dependence between how he moved in a step with how he will move in any other step, right. So, again we can say that this will be 0. Again you can say that by the same logic as earlier, when L will be equal to M, then we are multiplying two vectors which are the same. So, this must be equal to B square, and so we again have the same result where M now is the number of steps that he makes in the Drunkard walks, and again we do see the same relation I had earlier, and now this has to do nothing to do with the polymer chain, but now if I somehow associate each of the Drunkard step with certain number of carbons, for example, again we can see that we have the relation RE square proportional to the number of repeat units. Okay. So, what we are able to show you is there are two different kinds of model. One is a fiddly jointed chain and another one a one dimensional random walk or a Drunkard walk, and both gives you the same result, that the mean squared end to end distance is proportional to the number of steps, and that is what I refer to as an ideal chain model. Okay. So, what I will now show you is this idea is actually more general, and this will apply to even models which are like more elaborate than what we have discussed so far. For example, I can go to a two dimensional random walk and then also I will have the same result. I can go to more detailed chain models, starting to try to model the polymer chain in a better way, and again I will get the same result. The key message for this lecture is that there is a universality. We can build a class of models that all will give you the same result, the same kind of scaling behavior, the same kind of proportionality relation, and there will be a class of polymer chains which do show this behavior, and this has been proved experimentally. Many chains do show this kind of a ideal behavior, and this is what I will discuss in the next class. Okay, so thank you.